Let's do a sound check. Or I guess let's wait for YouTube to... Okay. Let's do a sound check. Alright, everything works. Every time I do a sound check and every time it works. But I am sure the second I stop doing that, things will break. Hello everyone, welcome to the Vulkan stream of this week, where, I guess the second stream, where we will bravely go where almost no one has gone before and start writing task shaders. But our goal isn't really task shaders, our goal is culling for meshlets. So let's see where we are right now. This is sort of where we left off last time, which we can render a mesh. We did a thing last stream, or rather yesterday, I guess, which has been the last stream, where we added meshlet visualization. Just to help us make sure that when we disable the mesh shader path, or enable it, it's actually different renderers, because otherwise they look identical. So the goal is as follows. Some of these meshlets, the ones you see on screen, are clearly visible, but there are also meshlets on the other side of the mesh that you cannot see, but we still process them. Now the GPU, I think we enable backface culling, hopefully. Let's see if that's true. Yeah, so we enable backface culling, so these triangles will be discarded by the GPU's rasterizer. However, it looks like on large meshes we are basically bottlenecking in triangle setup, which is the stage that would do this kind of rejection, right? Now, it's not clear if we can actually make things faster by doing some of these things ourselves, but the idea is that we will try to look at each meshlet and try to determine if the meshlet itself, like if all triangles in the meshlet are backface culled, should be backface culled. And if they are, we will try to discard this meshlet early. Now, I don't know what exactly the rates that we would expect will be, like in an average mesh, well-known stat, like half of the triangles are backfacing, but when you start dealing with meshlet culling, you can't cull a triangle one by one. You have to ask, are all triangles in the meshlet backfacing? And you should not expect as a result like 50% rejection rates. But we'll see where we can get. So our first step is we want to compute some data for meshlets that will help us tell if the entire meshlet is backface culled. And then our second step is use this data in a mesh shader to cull meshlets. And our third step is do the same thing in the task shader, because this should be more efficient than doing this in the mesh shader, and I'll go into why later. We will see how far we can get. I had a plan that basically involves doing that, and then inside the task shader you can use like atomic, so you can use subgroup operations to do this kind of culling, and maybe we'll get through all that and this will all be good, or maybe we'll get stuck at like generating meaningful data for meshlets and getting meaningful culling results, and that'll take the entire stream. I have not done any of these things before. As is usual with these streams, I have a general understanding of how things should work. I mean, I technically, I guess, I experimented a bit with culling, but it was never in a, like in an end-to-end context, where you also use the data to cull, and you look at the screen, and you are sure the results are perfect. So, we'll see how this goes. It will be an adventure for me, and hopefully for you guys. Let me... Yeah, alright. Wait, no. Whoa. Oh, how do I... Okay. So yeah, we did a bunch of stuff last time. So meshlet culling. Here's the idea. So you have a kitten, right? And there is like a part of the kitten that's like a meshlet with a bunch of triangles, and there's up to 126 triangles. but more importantly, up to 64 vertices in each meshlet. So it's a relatively small planar patch. Well, maybe not planar. It's a relatively small, hopefully connected set of triangles, right? You can see that like each color codes a meshlet. My hope is that we will not have to deal at all, like do anything with the code that generates meshlets, because based on the visual results, it looks like the meshlets are reasonably spatially coherent. In fact, before, like if we disable some code that helps us make sure that meshlets they contain triangles that are like close to each other, we get this, which means basically that triangles are semi-randomly assigned to meshlets. And in this scenario, I would not expect cone culling to work particularly well necessarily. But with this, I'm kind of hoping that the meshlets will just be okay and we won't have to do much. But for some of these, it's, like obviously some of these meshlets, they are super not planar. So why is planarity potentially important? So you have this meshlet with a bunch of triangles, and here's what you want. You want to ask, are all of these triangles backface culled? Meaning, are all of these triangles back-facing from the point of the view direction? So if you have a single triangle, and let's say, so now I'm switching to the sort of top, like view from the top, right? So imagine that we are looking at the camera and at the mesh from the top. So this is the view direction, and then let's say there's a single triangle, right? So triangle has a winding order, which you can use to determine the normal of the triangle. So it points like that way. This triangle is front-facing, and then there's some other triangle that is back-facing, and then there's triangles that are kind of almost front-facing or almost back-facing, that are almost parallel to the view direction. So like this triangle is, I mean, who knows? If the normal points here, then I guess the way I drew it, it's like almost back-facing, but not quite. So for each triangle, you can look at it and tell whether it should be back-facing or front-facing. And generally speaking, this is just dot product of the triangle normal and view direction. And if it's like positive or negative, then you get back-facing or front-facing. And if it's 0, then the triangle is exactly parallel to the view direction, which means it does not generate any pixels. So, oh, and remember, we are currently using orthographic projection, so things are slightly simple, although I think in perspective projection, this math is the same. But we won't need to care about this right now because we use orthographic, which slightly simplifies, reasoning. I don't know that it simplifies code, but it simplifies reasoning. So, here's what we want. So we want to say, here's a meshlet that has, let's say, 3 triangles that go like this, that have normals pointing in the corresponding directions, right? So in this specific case, all of the triangles are front-facing, but if you had another meshlet like this, right, and let me, so in this case, for this meshlet, all of the triangles are back-facing, right? And we want a really, really quick check that would tell us whether this is true. So we want to ask, hey, for all triangles in the meshlet, do all of them have a negative dot product with the view vector? To do that, we want to build a normal cone for each meshlet. So we want to say that for all normals, each normal is a vector, and we want to build a cone that is, like literally a cone of normal vectors, with the guarantee that all normals are within that cone. If you thought of normals as like vectors, I guess, that start from the cone's apex, then they all should be contained here, right? So the normal cone looks roughly like this, right? And the cone we will define as an axis, an angle, right? And then we can do the check. We can do this dot product check by asking if the view vector is, well, I guess negative view vector, but like whatever the signs are, is inside this code. And then what should happen is, so, well, not quite inside the cone. I guess it's slightly different because, well, no, this is, it's kind of the same thing. It may be kind of the same thing. So if you have a triangle, if you have this triangle with a normal, then we are interested, we want to say that the like negative view vector is in the half space sort of defined by this triangle. So if you have a second triangle that goes like this, with a normal like this, then we want to say that the negative view vector should lie in the intersection of these half spaces. So I guess we want to build the cone for the triangle normals, and then check if, and then kind of like add, say 90 degrees to both sides. So in this cone is almost at 90 degrees, but let's say the cone is kind of narrow, which is what we want. So then if we add 90-degree angle here and 90-degree angle here, we'll get a kind of like, I don't know if it's a cone at this point, but it's like a really wide, like inverse of a cone, right? And if the view vector is inside this like large, really wide, not quite a cone, then the triangles should be back facing or front facing or something. I don't know. We'll figure out the exact definition as we build this. But yeah, so the basic idea is we need to build a normal cone and then use this normal cone to do meshlet rejection in the shader. So we should have all of the information. Oh, I should probably have started with, so this was kind of got it right. So there's a couple of presentations that go into potential GPU side implementations of these approaches. Let's see if this has this. So this is a bit of a different approach that we are not going to use today. It's not ideal for mesh shaders necessarily. It's possible to implement this, but it's not as good. I forgot if this presentation goes into the detail, in the detail of the cone culling at all. There is a second presentation. Compute something. Yeah, that. Which is similar things but a bit different. This once again goes into a lot of the hardware specific details. I'm trying to see. Oh yes, so yeah, so we are talking about cluster culling. So yeah, we need the minimum closing code. Basically, we will not be computing strictly minimum and closing code. We will be computing some approximation for that, and then we'll see if it's good enough. Doesn't really go into the math at all, but whatever. So we'll figure it out. But basically, yeah, so there is like two presentations that you can look at to get some details on how these could work in games. I think some of the stuff has shipped in games, some of the stuff may be just research, but we are trying to do a similar thing with mesh shaders. So to start, what we need is we need to build a cone of normals for each meshlet. And so the way this would work is, for now, we will not really, like, our memory layout will be slightly suboptimal, but we won't bother. So we just want 4 floats that define a cone. The reason we need 4 floats is that there's 3 for the axis and then 1 for the angle, but we won't really store the angle of the cone. We'll store like a dot product or something. And then after we build the meshlets, let's add another function here so that we don't pollute the first one. Let me first remember to add padding to... Oh, I didn't. Oh no. Alright, phew. There was a stream issue? I don't know why. Alright, yeah, so we will... I guess I'm not sure what exactly got cut off, but I was saying we will add cone information to the meshlet. It will be 4 floats. We need to add this to the shader code as well, because we use the exact same structure on the shader side and on the C++ side. 3 floats will be the axis and then 1 float will be the angle. And now we need to compute this information. So right now we just added I like how this thing starts where we just add like 4 floats and then things explode. Oh, there might be an alignment issue. Now, I think I might not have aligned this structure correctly. There should be a padding. So this is unfortunate. This is kind of fragile. So yeah, so there's like, let's see, 378 bytes for this thing, and then 2 bytes for the other 2 things, and then no, this does divide by what? Oh, wait. All right, we did not go very far today before hitting our first issue. I'm glad I checked this immediately. What's going on? Let's do the math again. Maybe I didn't do the math right. So this is index data. Everything should be 4 bytes aligned, basically. This doesn't make any sense. Okay. Wait. Right. Okay, I'm not sure what the problem is. Let me... Like, I'm clearly running into some issue where the alignment of the struct is different between the CPU and the GPU. I'm just struggling to figure out why, because this shouldn't really happen. Unless this thing expands into something really weird, but it shouldn't really be the case. So now like everything is aligned. Interesting. Huh. This will be a problem if we can't store data for our code. I'm not sure I understand what is even going on. Why? Oh, our shaders. Oh no. Damn it. Okay. Yeah, okay. Alright. So the problem is, I understand. I was worried that I was thinking yesterday, would this be a problem? And then thought, hey, maybe things will automatically work. Things do not automatically work, damn it. Yeah, okay, so the problem is we added shader includes yesterday, but our shader includes aren't tracked by Visual Studio somehow. So we aren't really rebuilding the shaders, so when I made this change, the shader bytecode didn't actually get rebuilt. So that's unfortunate. Let's just rebuild it manually for now. Alright. Okay, let's continue. So yeah, so we need to build meshlets. To build meshlets, we need to add a function. I mean, we are building meshlets, but let's do like build meshlet cones or something like this, where we'll go over the already generated meshlet data and just, you know, compute these normals. We have two small problems. One is our vertex data is packed in half precision, so we'll need to unpack it again. And then the other problem is we don't have a math library, so I'll copy some code that like just works on floats so that we don't mess cross product order or something like that. So, but the idea is pretty simple. We just need to go over all meshlets in the mesh, and then for each meshlet we need to go over all triangles and then compute triangle normals. So let us I guess we don't really need vector 3. Yeah, so we need triangle normals, and there's like 126 triangles max or something. We will extract this stuff in a function at some point. So yeah. And conveniently the meshlet already has the indexing structure, because it has like a small index buffer, right? Okay, wait. Okay. So we can just load 3 indices of each triangle, and then we can load 3 vertices of each triangle. So we have an index of a vertex in the meshlet data, but then it points to the vertex buffer that we have assembled. So it should be like this. And then we need to compute the normal, but to compute the normal we have to decode half precision data. So let's do like half to float. We could have done some of this stuff earlier in the pipe where things are still floats, but that makes some of this code harder to sort of juggle. And then also we actually want to compute the cone data based on the same position data that the GPU would see, so that our culling results match what the GPU would do. So we kind of need to do this anyway. So yeah, so I have a Wikipedia page open where it says how halves are encoded, because I don't remember what the exponent bias is. But yeah, basically it says there's a sign, which is this, and there's an exponent, which is I guess there's 10-bit mantissa and then 5-bit exponent, right? So that's this. And then there's mantissa, which is this. And then if the exponent is 0, we won't handle like infinity values because we never have infinity values due to how our encoding works, I think. Hopefully we don't have infinity values. Let's actually check this. Infinity would be exponent. Yeah, infinity would correspond to this exponent, so that's not a problem. So then if it's 0, we need to do this thing. And we shouldn't have subnormal halves either, because our encoding doesn't produce subnormal halves. But yeah, so let's just say that if the exponent is 0, mantissa should be 0. And then we'll just return 0. Otherwise, we need mantissa plus 1024 extends this to like with a leading 1. And then we will just return. So we need the sign bit, sign -1 1, and then LDXF. Let's see. So this is a floating point value, and then our real exponent value is x minus 15. But then we could, I guess we could do this. But we also, yeah, whatever, let's just do this. So this matches the Wikipedia formula. Hopefully that works. We'll check if it does in a second. Well, like pi or something. So we are basically just trying to, maybe this function should be in Mesh Optimizer, but we are just trying to reverse the half transform that we are doing earlier in the pipe. Have to float. And then let's do the same thing for negatives. Anyway, yeah, so now that we have this function, we should be able to we should be able to just say things like have to float VA Vx, which should give us the floating point value of the x component of the vertex. And now we just need to compute the normal. I don't want to write a cross product every time. And one day we will add a math library. But since we don't have a math library, let's just steal code from some other place. Yeah, so this is basically saying that we need 3 floats for each vertex, which are floating point position. We don't really have a math library yet because we haven't like needed one. This is the first place where we need one. I think maybe next week we'll start doing some more camera stuff and we'll have to integrate GLM, something like that. Alright, yeah, so I don't know, in theory there could be triangles with 0 area, so let's protect against that. And then our triangle normal is that okay. So then after this we need to make a cone out of all of these normals. There are ways to make an optimal cone around a bunch of vectors, but they would take like the entire stream. So let's just average the normal direction and then assume that this is our new normal. In fact, we could do... No, yeah, this is better. And now we need to normalize the average normal. So we need basically the same thing again. Oops. Oh, yeah, okay, this is correct. It's not really area, I guess, average length. It's not really average length, it's the length of the average normal, but okay. This is what we get for not adding a math library. And I'm really hoping there's no types in this math. In theory, the normals could cancel out. That would be kind of weird. I don't want... So if normals... like, it could be that there is meshlet triangles that have... Like, if the meshlet is a cube, for example, then if you average all of the normals in the cube... If you add all of the normals in the cube, you should get 0, and then you try to normalize that, and you will not get good results. We can't really call meshlets like this anyway, but... let's just sort of handle this case. So otherwise... this... And then the final thing is we need a max.product. So we have built an approximate, average normal is our approximate direction of a cone. And then we need to compute like the spread of the cone, which will be just a maximum dot product between any other normal, the minimum dot product rather. Between any other normal and the averaged one. And the hope is that this value is close to 1. If this value is like 0, this means that there are some normals that are orthogonal to other normals, which would... so if you have two normals like this might still be fine, but basically the larger this value is, the better the cone is, because this means that the closer is the meshlet is closer to being planar, which maximizes our culling efficiency. Yeah, so we need another loop where we say normals I0, average normal 0. Oops. All right. And then okay, so probably this code, there's some bugs in this code, but the idea is we just store this data and then pass this to the GPU and then see if that works. So let's try to inspect. Let's first check if our half stuff worked. So yeah, this looks like pi. I mean, obviously it loses precision, but it seems like our code for half decoding is more or less correct. Let's just, you know, Okay, yeah. So this looks reasonable to me. Now let's see how bad our cones are and if our cones even make sense. Okay, so 0.91 is a pretty good cone. So I was saying the closer the value is to 1, the better it is. So this is pretty reasonable, hopefully. 0.8 is not 0.7, so 0.3 there was like a cone with really bad. But this is expected. There will be some meshlets that have a lot of triangles, that have triangles on like a curve. So you will not be able to efficiently do backface culling on this. In a production setting, you don't do just backface culling. Backface culling should get you like, you know, double-digit percentages, but small double-digit percentages. Like I'm hoping for like 10-20%, I guess. 20%. I'm hoping for 20% reduction in triangle count. Oh, it will be hard for us to compute the actual reduction in triangle count because we don't have a profiler working, we don't have a debugger working, like nothing works. We could add a pipeline query, but anyways, it will be not super easy for us right now to figure out how efficient our culling is by looking at numbers, but we will do this at some point later. Yeah, so then in reality you should also compute some like a bounding sphere or something for Meshlet, and then you can do occlusion testing, and then you can do frustum testing. So that we will get to at some point on these streams, but definitely not today, and definitely not next week either, because you need a depth buffer. We don't even have a depth buffer. All right, anyway, so it seems to me like maybe our code works. It's hard to tell, as usual with these things. I mean, we can like double check. So for this meshlet, we have an average normal that's basically 0, -1, 0. And let's look at so there is 79 triangles in this meshlet. And let's just look at the, yeah, so you see there hovering around 0, -1, 0. There are some that are kind of not close, like this one, right? Which is probably why our minimum dot product for this one is pretty bad, right? But this is not terrible. It could be that with an optimal mesh cone construction we could get better results. All right, so now the question is, what do we do with this data? So we have uploaded this data to the GPU, we aren't using it yet. So here's what I want to do. I want to first check if early returns from a mesh shader even work. Let's say, let's arbitrarily say that if the meshlet index is less than, how many meshlets do we have? So we have like 300 meshlets in this mesh. So let's say that if this is less than like 150, we'll just return. I don't know if early returns are a touchy subject for shader compilers. Let's see if that works. Okay. So this is kind of what we want to do, but we want to have a better condition that doesn't just throw out half of the meshlets. So now we'll need to do some math because we need to figure out, the thing I wanted to do is, it will be hard for us to figure out if our culling works if we cull backfacing triangles, right? Because backfacing triangles are already culled by the rasterizer. So I want to do is I want to temporarily switch the culling here from back to front. I don't even know if back and front are correct right now. It's really hard to tell. I don't know which way the mesh is looking Oh, I guess I can kind of know. Well, so we are outputting the normal, and so this normal is basically 1, so it's like close to 0, 0, 1, which means that it's pointing in the z direction, and z direction goes inside of the screen. So this should be the backface of the mesh, I think. So I think this should be the backface of the mesh. Now our goal is to remove meshlets that we think are backfacing, and the hope is that a lot of these will disappear before even reaching the rasterizer, right? So for this we have to basically have a function that takes like whatever that takes the cone that is 4 floats, I guess. We can just what is this data? And then takes the view direction and then does something with this. And then our view direction right now is is hard-coded, right? We just have an ortho projection with the view direction basically being plus z axis. So this should be just if cone test or not cone test or something. Let's call it cone cull. If cone cull of meshlets mi cone 0, 0, 1, we will do an early return. Okay. All right, and now we just need to implement this. Dear God, what's happening? Oh, vec4 is 16-byte aligned or something like this. All right. We should make sure that our meshlet structure is 16-byte aligned, but for now, let's not do that. Or actually, maybe we can do... It's painful to balance, like it's painful to always keep these things in sync, because GLSL and C++ use slightly different packing rules occasionally. They're like close, but yeah. Like I can't ask GLSL to align this struct to 16 bytes, I think, unless I have a 16-byte aligned member inside it. So I could just say probably vec4 cone, and then here I could probably say align as 16, and then maybe this will work. Yeah, it's slightly fragile because if I remove this vec4, then this thing stops being aligned, and the other thing is, and I can't do align as here because that's not valid GLSL. Anyway, let's leave this like this for now. Yeah, so how do we call a cone? Let's try to work that out, shall we? Let me also double check that the stream quality, okay, stream is fine. So we have a bunch of, so basically we need to do the thing that I was talking about where, so there is a cone, right? So there is an axis of this cone, and then there is the dot product that basically defines the angle of the cone. So if this dot product is 1, then the angle is 0. If this dot product is 0, it's the cosine of the half angle or something, or like 90 minus half angle. Doesn't really matter. So what we want is to ask, are all of these triangles definitely for sure backfacing, right? So are all of the vectors inside this cone, if you did a dot product with the view vector, would it always be negative, right? So the way to do that should be that we can take the let's see. So in a extreme case, I mean, yeah, I guess basically I just want to extend the cone to add like 90. Yes, okay. So let's try to do this more rigorously. So there is this alpha, which is the cone's half angle, right? And then the dot product that we have computed, this should be the cosine of the of alpha, I believe. Yeah. So when when alpha is 0, then this dot product is 1, right? When alpha is 90 degrees, which is a pretty bad cone, because this means that it's like a degenerate cone that sort of looks like this, right? Then we get cosine of 90 degrees, which is 0. So the thing that we want is that I was talking about this in the way that we add 90 degrees to both sides of the cone, essentially extending, instead of alpha, we'll get alpha plus 90, right? What this gives us is this. So if the view direction is inside this expanded cone, then the triangle should be backfacing, because the idea with backfacing is like a triangle is backfacing when the angle between the normal and the view vector is basically 90 degrees or more, right? Because if it's no, it's like between 0 and 90, like 90 degrees or less, I guess. So to get this like 90 degree cutoff, we could expand the cone to incorporate these extra sides of the cone that are plus or minus 90 degrees, and then just check if the view vector is inside that or not. So our test could just be that if the dot product of the cone's axis and the view vector fits inside the expanded cone, the cone test should go like this. Then we should be good. But this value is the value for the sort of expanded bounds that are the bounds of the cone plus 90 degrees. So for that we need to compute, we have cosine alpha, and we need to compute cosine alpha plus 90, which should be like sine, right? And I can never remember these trig identities, so let me Google them. This one. I could like I usually do this math like manually, but it's weird to do this math manually. Yeah, so cosine 90 minus phi should be sinus phi, cosine, therefore cosine 90 plus phi should be sine minus phi, which should be minus sine phi. So this should be this. And this should be like this, but it's painful to do this. I kind of want to pre-compute some of this stuff on CPU, partially because, so if the cone's angle, so I was drawing these pictures with small cones, right? So if the cone's angle is 90 degrees or more, of the normal cone angle is 90 degrees or more, this basically means we cannot call this at all cone's half angle, because like if you take this degenerate cone that I was drawing here, right, and expand it 90 degrees in both directions, then you get like a full sphere, full circle, right? Which means that whenever the view vector is, it's just not, like you cannot call this, it's always, you can determine if it's back facing or front facing. It's like a triangle in this meshlet might be front facing, right? Which means that once our minimum dot product is below 0, kind of all bets are off, we can't call anything anyway. Yeah, so I want to keep this computation as is here. If I just run this, it will not be correct because we are not doing the right sort of cutoff. We are not computing the right cutoff. So I want to compute the right cutoff on the CPU. So instead of min dot product, it should be like cone W or something like this. I don't know. And so the idea is that for cone to be backfacing, the angle between view vector and cone axis should be less than should be more, less, should be more, I don't know, less than cone half angle plus 90 degrees. That definitely is not correct. Let me, it's all right. Let's write a comment later. I feel like basically the answer is this with a minus sign, right? Which is what we have computed. The problem is if min dp is below 0, then this is not quite correct because we should just say like -1 or something. So if minimum dot product is less than or like say equal to 0, then it should just be minus wait. Yeah, so it should be this, I believe. And then if minimum dot product is 0, sorry, if minimum dot product is 1, this means that all of the triangle normals are the exact same as the cone apex, like the cone is degenerate, right? Which means this value will be 0. And then this will call everything that is back-facing because dot of view and cone. Well, it's confusing because like view points sort of at a triangle, and triangle for the triangle to be back-facing, they should look like the triangle and the view vector should point in the same direction, not the opposite directions, which means some of these math and science confusing. I feel like this should be the solution though. So I mean, who knows if this is correct? There's clearly some of the meshlets that it's unfortunate that we don't have a way to rotate camera or mesh, because if we did have a way to rotate camera or mesh, it would be easier for us to figure out if the code that we just wrote is correct. However, I feel like the code that we wrote might be correct. I'll have to double check this math. So you can see that we like the intention was to have as few pixels on screen as possible, because we are sort of doing front face culling, so only back face cull triangles are rendered on screen. So the more triangles, the more meshlets we can cull away, the better it is. You can see that we aren't succeeding for every single meshlet, but this is actually expected. So the meshlets that are on the boundary of the mesh, they have some triangles that are front-facing and some that are back-facing, so we can't make a good determination. There are some meshlets in like the center, like these guys, but they might be, this one looks like it's around the nose area, right? So it will have like a curvature like this or something like this, which means that some of these triangles, like the normals of the triangles, point in a lot of different directions. So I feel like this might be correct. I think this should be the correct math. So let's do this again. And I should really do, floating point is really unforgiving. If minimum dot product is 1, well, no, I guess in this case I should be fine. I was gonna say that in theory this could go below 0, but this is actually not true because we have a strict comparison here, so we should be fine. But yeah, so if the cone is really small, then minimum dot product is 1, because this means all of the triangles are aligned in, they have normals that point roughly in the same direction. So then we do a square root of 1 minus 1, which is 0, and then we get this value as 0. And then here we are saying if the cone direction that, for example, points away from the camera, and the sort of negative u direction which points at the camera, if the dot product is less than 0, the other way to phrase this is, I guess, this, which should be the same computation. I just moved the minus sign out and sort of flipped this. This should be the same thing, right? Which could mean that we can pre-inverse this guy, right? And this is nicer because if we wanted to pack this, now this guy is always a positive number, so if we wanted to pack this in 8-bit integers or something, which we might want to do at some point, this will be more efficient. But yeah, so if the cone, if all of the normals of the triangles point in the same direction, then the minimum dot product is 1. The square root, which is actually just the sine of the angle, of the half angle, or the cosine of the half angle plus 90 degrees, is 0, right? Because it's 1 minus 1 squared. And then we are just saying that the cone test is the dot product between the view direction and the cone axis is greater than 0, which is the backface culling check that we have talked about at the very beginning, right? Like this is the side of this. Now, if you have a cone with a wider angle, then this value will get larger, right? So there will be more cones that have a dot product that's like more than 0, but if it's like 0.1 and the cutoff is 0.2, you will not call these. And this is kind of what is happening in these meshlets that we aren't calling. So I feel like maybe our code works. It's hard to say, but maybe our code works. It's hard to say because we don't really have a way to rotate meshes or cameras or anything like this. Like ideally we would maybe like spin the mesh and then and if we were to spin the mesh, then we would basically need to transform this cone axis by the world matrix of a mesh, right? But for this we need to pass some extra data to this shader. For this we need push constants. We haven't talked about push constants, so they don't really work. So I don't know if I want to do this again, because I think we have culling working. Let's check if this is true on a larger mesh. And if we do have culling working, then I want to try to use task shaders to do this culling instead of mesh shaders. But let's first see if it actually works. Oh. How curious. Oh, early return doesn't... Oh. So this is interesting, right? Early return was a bad idea, I think, because we forgot to set the primitive count. I hope this is what it is. Oh, well, whatever. Okay, good. We aren't culling a lot of stuff in this mesh. That's unfortunate. There's some objects, there's some meshlets that are being called, but there is not a lot of them. This is surprising. I would think that it should work. Let's check that our code actually works on, let's see if there's like another mesh. Oh, right, so in this mesh we are seeing sort of multiple layers of the mesh. So yeah, so it's hard to know if this is like Stanford Dragon, but it's not. Let me see what kind of meshes I have. We can sanity check. This mesh is probably too big. It's like doesn't fit in 0-1 boundary. Oh wait, I mistyped the mesh name. So this looks like, let me. Yeah, so basically it's unfortunate that, oh, you know what, let's do this. Let's just do the same thing on CPU, so that we have stats, like from this direction that we are calling things, how many triangles would be called. That should be easy to do. So so we need to do a dot product between basically cone. We need to do a dot product between the cone and the 0,0,1 vector, but the 0,0,1 vector is canceling out two components of the dot product. So it should just be, this is our cone test for the 0,0,1 view direction. And let's just print this. So that we have, I said at first that I want like 10% or something. So this is more than 10%, so this is good. Let's look at Buddha again. So this is less than 10%, this is like 2%, so here it doesn't work very well. Which might mean that we are not doing something right, or it might mean that our clusterization algorithm is not working as well on this mesh, which is also possible, or it could mean some other things. Let's look at the dragon. So here it's, what is it, like 3%, right? So yeah, not amazing. What was it on the kitten? On the kitten, it's pretty good, right? It's like 30%. So it depends on the connectivity of the mesh. I think it could be that on the Happy Buddha mesh and on Stanford Dragon, either clusterization. Oh yeah, no, wait. Right, I remember. I think this is the problem. Yes. I thought about this problem before, never mind. Yeah, so this is sort of expected. So remember, this technique isn't supposed to be like a end-all be-all of mesh culling. You should really, this is really simple to do, in the sense that on the GPU, our test, as you have seen, is just a dot product, right? And you need to transform this vector by the world matrix, but still you don't have to do this. Like, you can pre-transform view based on the inverse view matrix. But fundamentally, this test is really cheap to do. A more expensive but more interesting test is definitely occlusion. If you have a large mesh and you can build some sort of occlusion buffer, which we will get into later, you can do occlusion tests on the sort of bounds of the meshlet, and that's much nicer. But yeah, so this thing that we wrote right now, it seems to work reasonably well on relatively low poly meshes. Like our kitten has how many? 30,000 triangles, right? So this is like what you would expect from a like in-game character. Oh, I have a real model of a game character that might not fit on screen. Yeah, it clearly doesn't. So yeah, here it doesn't really work that well, but it depends. So basically, sometimes this can work well, sometimes this doesn't work well. What's that? Yeah, so you have to have enough triangles so that a meshlet can be backfacing, but not too many. So it's slightly fragile in that sense, but that's fine. We will do other types of culling in the future, and on some meshes like this kitten, it works really well. So if you imagine a scene where there's a lot of these guys, then this can work pretty efficiently. So why does it not work very well in high poly meshes? Here's the problem with high poly meshes. Here's what we are doing. There's a meshlet that is basically a local patch of the surface, right? So and then we are saying the normals of these triangles in the meshlet should point roughly in the same direction. The problem is in high poly mesh, there's a lot of areas with really high local curvature. So where in a low poly mesh you would see like triangles like this, right? In a high poly, and then extra detail is modeled with normal maps or something. In a high poly mesh, the extra geometric detail is modeled with geometry, so you see like this, right? And the problem here is that the normals of these triangles point in basically a lot of different directions at once, which means that it's not as efficient to do backface culling in batches, right? Because there's just too many conflicting directions for each batch, which is why we got like a few percent of triangles culled on Buddha, right? Because it's just there's a lot of areas that are small, but they have high local curvature. So this is what I think happens. Anyway, let's actually check now that our code actually works. Because if we flip back the culling to backface, we should not see, remove the debug code. And then yeah. So when I switch between the traditional render path and the meshlet path, nothing disappears, which seems to suggest that maybe our code works. Because now it's culling backface patches that we don't see anyway. So that's good. It's slightly unfortunate that on high poly meshes it doesn't work as well. Like the real scene would have many objects, and then if for each object the culling works reasonably efficiently, then it's good. But we don't have many objects, so it's hard for us to measure GPU time, right? But we know the solution to this. So let's temporarily use the solution to this, which is just draw the thing more than once. All right, so we draw 1,000 kittens? So 1,000 kittens with RTX path render in who knows what, 5.4 to 5.6. With the traditional pipeline it's 5. Who knows what, 5.7, I don't know. So it doesn't look like we are really saving time, even though we are calling a lot of meshlets out. Here's one theory as to why this happens, and here's why I wanted to use task shaders in the first place. So the way this code works is that we do some, not that much math, but well, our memory layout is really not good for this kind of culling right now, because we have we are reading 16 bytes and then there's like a giant blob after this that we are ignoring. So that's not optimal, and we can fix this. But here's a problem. Here's another problem. Another problem is that the main function for the mesh shader runs the mesh shader warp, which has 32 threads, once for each meshlet. This code runs for each thread in this 32 thread work group. And it's not doing much, but this other code isn't doing that much. There is like 4 loops here, but this for loop has basically 2 iterations in it. So we are saving time, maybe, but if you imagine a more complicated test here, where we do occlusion culling, where we sample from some like occlusion buffer, from depth buffer, etc., do bounding sphere checks for frustum, all of this stuff right now runs the same computations on all 32 threads in a warp, which is not great for performance. And I say all of these things, not great for performance, but the problem is it's really hard to measure if we are doing anything useful with this cone culling stuff at all. Oh, should we try, I'm wondering what would happen if we didn't have backface culling. Alright, so at least we are saving time. So if you disable backface culling in the rasterizer, you can see that with the RTX path on, we are like 7 milliseconds for 100 or 1,000, I forgot, 1,000 kittens. And with the traditional pipeline, it's like 9-ish. And then if we disable our beautiful test, syntax highlighting doesn't really work, then you can see that it's roughly the same time, right? So if you don't do rasterization backface culling, then we are saving time. If you do rasterization backface culling, then we might be saving time, but it's like in the noise, so it's really hard to measure correctly. So that's slightly unfortunate. But anyway, so let's look at the task shaders. If only to, at this point, I guess I'm not expecting to see amazing wins from the task shaders because our test is so cheap and our perf difference is so small. But maybe we will see some difference. It's hard to tell. Yeah. Before we start doing task shaders, let's commit the stuff that we have written today. And yeah, the memory layout here is like, if our mesh shader is spending time like reading data from random locations in memory, then this will not be very good for anything really, for task shaders as well. We can fix this, which requires different layout for the meshlet structure, but I don't want to fix it right now. There's this draw count thing. Let's temporarily change draw count to 1 so that we can submit this with just 1 kitten. All right. Alright, so day 8, cone culling. We have implemented Meshlet cone computation, and we can successfully, I think, cull entire meshlets in the mesh shader based on this code. Culling efficiency is reasonable on some meshes, but deteriorates on really low poly meshes or really high poly meshes. It's not like a property of high poly meshes per se. Like if you just took a low poly mesh and just tessellated it highly before applying displacement mapping, then it would still be good efficiency. In fact, better than what we are getting now, probably. But once you start perturbing the surface, things sort of don't work as well. Which seems expected, as it's just a limitation of the cluster culling technique. I've done some experiments before where if you compute clusters a bit differently, you should be able to get better culling results, but it's hard to say how much you can do this without compromising performance elsewhere in the pipeline. Let's see if I can find this. Search is really good these days. Let's see if we have data for our kitten here. Oh, we do. So yeah, so this stuff is sort of not super practical for meshlets. And the only thing that's really practical is these variants. And they all get around 27% on the earlier tests that I've done. Let's see what we are getting now. 24%. I don't know if the code that I wrote for these tests was actually really correct or not. It's hard to say. Oh, the thing is, these clusters were smaller. I think they were 64 triangles. I think 64 here refers to triangles. So maybe that's also expected. Let's see if, so we have submitted our code. Let's see, just sort of out of curiosity, what would happen to our Happy Buddha culling rates, which right now are really not that good. Now we are getting to 7, 2, and 4. This is like 3%, right? So that's 2.5%. That's not good. But our clusters are pretty large. Let's try to see what would happen if we generated up to 41 triangle. So this is like slightly less than 10%. It's interesting that I was getting more interesting numbers in the earlier tests that I've done. It could be that the clusterization was better, or it could be that these tests weren't really valid because the math wasn't really correct. I'll have to dig that out and check later. Anyway. Alright, let's close all that, close this, we don't need this anymore. When in doubt, render more kittens, exactly. Oh, did it reload? Alright. I'll have to analyze. The results on Buddha are slightly surprising. I'm worried that we might either be not doing something correctly, or or else, because I knew that the technique has problems on high poly meshes, but I didn't expect the problems to be that severe. It's really hard to tell. Well, this is a different part of the mesh, so this is the front face, and these and our culling works in back facing triangles. There is a lot of noise in some of these areas. This is a scanned mesh. I believe this is like 3D scanned, so it could be that there is high deviation of normals. I'm just surprised that I didn't see this to that extent in my earlier tests. But could be that my earlier tests just weren't correct because they weren't using correct math. But this is basically stuff that could be improved later. We could double check the math, etc. So let's try to write a task shader. We are a bit more than an hour in, and we have a bit less than an hour left, or maybe like an hour. So task shaders. So why do I care about task shaders again? Right now we are calling meshlets inside the mesh shader, which is not a great place to call the meshlet in, because this shader runs, there's 32 threads that run for the entire meshlet, right? And we want to run this test in parallel. So to call in parallel, we'll need a task shader. Task shaders can, task shader is like a compute shader, like a mesh shader, similarly to that can run multiple threads, and then it can produce dynamically waves of, or warps rather, of mesh shaders. So that's kind of cool. And when you use task shaders, you basically are supposed to use a task shader and the mesh shader, and the task shader says how many mesh shader workloads to run, and the mesh shader actually computes the vertex data. To do that, we need a task shader. To do the task shader, we need to slightly tweak our code, because we need 3 shaders now instead of 2, so we need the task shader, vertex shader, and fragment shader. So I wanted to do this thing last stream, but we didn't get to this, but let me just do this. I'm gonna basically, instead of just specifying 2 shaders, I just want to say here's a list of shaders, and just like, you know, use all of them. So for that, we will use another C++ feature that seems to fit. Oh, should be used yet more. I think in C++ you could now do this, which is like a type def, but it has the correct left to right reading order, which is nice, so let's do that. So basically whenever we pass 2 shaders, I'm going to pass a list of shaders, and this will make it easier for us to, like, we'll just add it. We'll be able to add the task shader without modifying these functions to add a third optional parameter. And then what if we need one more shader stage, or what if we want compute? For compute you only want one shader stage, one shader, but here we're specifying 2. So it's kind of a thing that I wanted to do anyway, so let's just do this now. I don't know if you're supposed to pass initializer lists by value, by reference, or what, but I don't care. It's a list of pointers, so even if we need to copy this, I do not care. And then we just replace everywhere where we're using 2 shaders, we just have a loop now. The code that I'm modifying now, we have written yesterday on stream. If you haven't seen the stream yesterday, then you are welcome to take a look at the video recording that is up on YouTube as usual, where we used descriptor templates, and we also parsed spear vblobs, which was pretty painless, really painless, and basically just worked. So yeah, so this code tells the driver how many stages, like which stages use the storage buffers in, so that just passes that through. the same thing. Yeah. So we don't need to hard code the vertex and fragment stuff anymore. And whenever we create a pipeline, we need an arbitrary number of stages. Stages size, stages data. Pipeline shader stage create info stage. Okay, so that's it, I think. And then we obviously have to change the calling code, wherever it was, where we were previously just passing two shaders, and now we have to pass a list of pointers to shaders. So that is nice and simple. And we might do some further refactoring to some of the stuff later, where we like add something like a shader program or something like that, so that we don't have to repeat a bunch of the stuff every time. Now this is good enough. I'll also switch to debug mode so that we know that we are not breaking validation. All right. Oh, and okay. So did I say day 8 in the previous comment? Minor shader refactoring. Now use shader initializer lists to pass shaders to the functions that need them. Let's see. Yeah, we said day 8. That's good. All right, so task shaders. So here's the simplest way how a task shader might work. And I want to start with that. So task shader is a compute shader, which means that it will have to, sort of compute shader, which means that it will have to run several threads. Let's just say that it will run 32 threads. So here's the first thing I want to do. I want to make sure that the number of meshlets that we have is rounded up to 32, which isn't really necessary, but again, we don't really have push constants working yet, so I don't want to deal with that right now. So let's just say that to do, we don't really need this, but this makes sure we can assume that we need all 32 meshlets in task shader. And this is basically just while meshlet size is not divisible by 32, just push a dummy meshlet with 0 vertices, and that should work even right now. So we don't really need this long term, but today this will make some things easier for us. So now here's the simplest possible task shader that you should be able to write. Let's copy that. So we'll add a task shader, and then let's add this to Visual Studio. So we want a bunch of extensions. It's like the same usual stuff. We want to run 32 threads. We will need access to Meshlet data. Note I'm keeping the binding one. We wrote code yesterday that in theory should just make everything work with that. And then the only output of a task shader, and I have a spec open somewhere, is the only built-in output is this guy. So what we want is we want to say this. So there is 32 we will be spawning a task. I don't know how to call these things correctly now, but okay, so we are spawning, let's say we are spawning a task for each 32 meshlets, and each task will request to run 32 task count, number of mesh shader tasks. Should I say task groups? So we'll spawn 32, so we'll spawn a task group, I guess, with 32 tasks for each mesh, yeah. Anyway, so if there is like 32 meshlets in our mesh, then we'll spawn one warp in a task shader. And then each thread of this warp will process one meshlet. And then at the end, it will say, hey, can you please run every meshlet that survived the culling process through the mesh shader pipeline? So for now, we will just not do culling. We will just say that, I guess it's the same thing where TI was meant to say thread index, but now there's also task index, which is weird. But okay, let's just, for now, keep it like this. So each task will just spawn 32 mesh tasks. Each task shader task will spawn 32 mesh shader task. I feel like I should read up on this terminology and actually use the correct one, but hopefully it sort of makes sense. And then I'll need to do one more thing, but let's just write this code first and then see if that works. So wherever the, well, yeah. So whenever we draw the mesh, we are saying we will use one task warp for each group of 32 meshlets, right? And then the task shader will do the amplification where it will say, oh, hey, can you run 32 mesh warps now for this, right? And obviously we'll need to compile and use a task shader. So let's do that. Task. It's really convenient that these like mesh, vertex, fragments, and task all have non-overlapping first letters. So that's nice. And then we will need to add task shaders are before mesh shaders in the sort of pipeline order. Oops. And yeah, so this is the refactoring that I was talking about. I had to add task shader in 3 places. I would like to add task shader in like 1 place, but that's fine for now. Okay, so that's that. That's like a dummy task shader. It doesn't actually do culling. This will not work. Let's check if it works in the way. If it doesn't work in the way that I think it doesn't, it shouldn't. Oh, yeah, okay. This will super not work because we aren't even compiling the shader. Okay. So now this will not work in the way that I am expecting now. task shader is not supported, right, because we haven't enabled it. You have to explicitly request all features that you need. The extension wants you to separately request support for task and mesh shaders. I don't know why this is true, but I'm guessing maybe they anticipate some future where some GPUs that are not NVIDIA GPUs support mesh shaders but not task shaders or something like that. I'm not quite sure. All right, yes. So this does not work in the way that I expected. The reason why this does not work, once it passes validation, is that we are saying run 32 mesh workloads for mesh warps for each group of 32 meshlets, which means that in our mesh shader, this meshlet index will be from 0 to 31. So we want to add an offset here, right? So we want to add basically meshlet offset. And this offset we have to pass from task shader to the mesh shader. You should be able to do this by using task NV, I think it is. Variable. So we will pass this variable from from task shader to the mesh shader. Should also only one thread. I guess only one thread should write this, right? So I'm guessing that this is what it should be. So I think this is how it should work. Task and V variables can only be declared as blocks. Okay. I don't remember the syntax for this, so I don't really know what it wants from me. Yeah, block. Okay, I don't know if this is correct or not. I'm not a GLSL expert, but let's assume it is. So hopefully get the same error here. Yes. All right. All right. Okay. Okay. So that works. So that's nice. So our task shader isn't doing anything useful, right? It's just saying, hey, for each 32 meshlets, can you run them? Here's a question that I don't know the answer to, that I'm really curious to learn the answer to. The fact that we just added a task shader that does this like relatively minor amplification, like 32, does it make things slower? Let's answer this, shall we? So, this runs. Wow. Why does it run so fast? Wow. I did not expect this. What did we do? Are we still doing the 40? Is that the thing that we changed? Did I forget to undo that? Wow, what? No, wow. So, this is faster than I remember. This is rendering at 0.1 millisecond versus 0.2 milliseconds roughly with the traditional rasterization path. It used to be the same. Is that task shaders that's doing that? Or is it something else? Wow, what? This is super unexpected. Okay. Okay. let's stash this work that we have just done. And run this thing without the mesh, without the task shader. Wow. Wow. I am shocked. I do not know what happened. Huh. So we are running way faster with the task shader that does nothing than traditional pipeline. So we are finally starting to get benefits from the new mesh stuff, but I do not understand why. Whoa. Let's try to render. Whoa. I don't. Is it the case that when you don't use a task shader, NVIDIA makes a task shader that just does a one-to-one remap, like spawns one mesh workload from the task workload, from the task warp, and this is really inefficient because like there's some hardware limits that it's hitting, and we just spawned 32, so it's way better. Is that what's going on? We can check this. So 10 Buddhas render at basically 195 or something. Huh. I mean, I'm happy that we are starting to get the benefits performance-wise of the RTX path. I'm just not understanding why it is the case. So 10 Buddhas with the task shader that does a 32 expansion. Yeah, like 1.4, right? 1.35 maybe versus 1.95. That's substantially faster. In fact, these are the gains that I was expecting all this time because of a higher vertex reuse ratio that I just wasn't seeing, and I didn't know why. Wow. Wow. We didn't even call, I mean, we are doing culling in the mesh shader, but on Buddha it doesn't matter that much because there's very few meshlets called. Interesting. Okay. This is curious. I mean, it's fortunate but curious. So here's the question then, right? So maybe is this what the basically NVIDIA driver doing? It's saying, hey, if you don't use a mesh shader, we'll just proxy the mesh shader work like this, like one-to-one. This is slower, but still like faster than not using a task shader. So this is really interesting, right? Yeah. And then traditional path runs at like 2.1, right? So if you don't use the task shader, we are like a tiny bit faster, like 5% maybe faster than traditional rasterization path. If we use a task shader that's just doing one-to-one mapping, then it's like faster. And then if we are doing the thing that actually makes sense, which is like 32x amplification, then we're running really slow. What did I do? Oh, oops, yeah. Yeah, okay. All right, I did not expect this at all. This is surprising. This might mean that there is a path that does not use a task shader but does use a mesh shader that is not very well optimized, because it's super weird that we were adding a dummy task shader that just did one-to-one, which didn't really require, other than the offset, it doesn't. Oh yeah. So like if we do one-to-one, then we don't even need the offset in the mesh shader, and it's running faster. So this is surprising. Is anybody from NVIDIA watching the stream? If anybody from NVIDIA is watching the stream, I would be really interested to know what the hell is going on here. This is really cool that we are getting the benefits. Like, I just don't understand why I need a task shader to get the benefits with a dummy task shader. Anyway. Alright, so, okay. Cool. This was weird. Alright, but whatever. So here's what we need for culling. For culling, it's not enough to just pass an offset. For culling, we don't really. For culling, basically, what we need is we need to pass indices of meshlets that we want to use. So let's do that without culling. So we will be asking our mesh shader nicely to process 32 meshlets, up to 32 meshlets, really, right? And then for each thread index, we will basically be doing this offset math, like this, and then filling the task count. So this is the more general, this is what will let us then not fill some of these indices to do culling. Meshlets 32. And then here, instead of meshlet offset, we will be just saying, let's get the index from the task memory. Oh, oops, yeah, let's call this that. Meshlet indices. Meshlet indices. Meshlet indices. Okay. So this still runs at like 1.4. So that's good. So we didn't really lose time on this. Okay. All right. So now I want to switch back to the kitten. Why is this again in the wrong folder? Visual Studio is like, oh, whenever I add like a custom build step, Visual Studio decides to just move this out of my folder, which is weird. So yeah, so let's just switch back to, we are drawing one one kitten, and then we want to enable debug mode here so that we see the mesh. And then we want to go back to the front face culling, so that we can see our culling work. Okay, so now let's move the culling from the mesh shader to the task shader. Because we don't really need it here anymore, because hey, task shader is now guiding the mesh shader, so we can just move this code. So we don't need this here. We need this thing here, and then we need here to do culling on a meshlet, and then if the result is, if we do need the meshlet, like so if cone cull does not fail, then we need to add the meshlet to yeah, so this is where it's getting confusing, because this is not really meshlet index. This is like meshlet group index or something like this. And then meshlet index is really MGI times 32 plus TI. And then I will do, I guess, this, right? Yeah, okay. So I just removed the culling for now, right? So now to do culling, we need to do something here. So to do this something, we need to say, hey, wouldn't it be cool if we could add the meshlet to this index block? So the thing that we will do first, which is probably not very optimal, but we will do this. So we'll declare a shared variable, which is like meshlet offset or something, which is a different offset really. So let's just call it for now meshlet count or something like this. That starts at 0. Then every thread, so we have 32 threads, 32 meshlets, each thread calls one meshlet. For each thread we are doing the cone test. If the cone test succeeds, which is to say cone culling fails, then we will ask, hey, can you give me an index that is a result of basically adding 1 to meshlet count. And this is why I had atomic add page open. Yeah, so basically memory and data. And atomic add should return, what does it return? Returns the original context before. So this is the traditional, you know, like if you are writing C++ atomic code that like pushes data to a shared buffer from multiple threads, this is the exact same code that you would write in C++. So, so we are asking, hey, can you increment count by 1 and give me the old value, which gives each thread an index into this meshlet indices buffer, where you should write the index of the meshlet to render. So now we just need meshlet indices of index equals some I. So this will ask the mesh shader to render the meshlet, right? And now here we will need to specify the count of things that we have written, which is just the meshlet count. And there probably should be some sort of barrier here, probably. Can't initialize this, so I guess I have to, do I have to do like this? I guess I can initialize on all threads as long as there is a barrier. Ugh. Okay, so our culling still works, so this is nice. I feel like we are missing some memory barriers here. I have never used GLSL atomics, so I have no clue what the rules are. The rules are different arbitrarily between different APIs and stuff. I also don't know, can I initialize? Can I like move this here, or does that not work? Not allowed in nested scope. Does it start from 0 like automatically, or do I have to do this? Maybe I have to do this. Let's figure out what the atomic barriers are. No, I don't want atomic counters. Yeah, memory model. Memory barrier. So I want some sort of memory barrier. Yes, I feel like I want this guy, or creates visibility for all incoherent. I'm not sure. I feel like this is the one I want, but I don't really want to read the spec to tell me. Yeah. So I think what I want is this and this. And I mean, our code still works. So the idea is this. This initialization is done, so we have 32 threads that concurrently run the main program. All of these threads concurrently execute this operation, which doesn't really matter because, I mean, we could like add like this, like so that only the first thread does, but it's probably not really important. I'm not sure, but it's probably isn't. Oh. Yeah, no, yeah, this is correct. It probably doesn't matter. In fact, I don't know if I need to do this here. I was doing this in the mesh shader as well. I don't know if I need to be doing that. I might not need to be doing that. It might not matter for performance, but like an if condition that we don't need, I don't know. Anyway, so all threads concurrently write to this value. Then all threads wait for all threads to have all shared operations complete. Then we are doing the cone test, we are doing an atomic add, and then we are writing to an index somewhere. But then what could happen is that the thread number 0 that runs like this, writes this variable, maybe in terms of memory model, it could get to this code before some other thread has completely incremented this value, and this value isn't visible to the thread 0. So this is why we do this here. Now what I'm expecting is that on NVIDIA, with 32 threads in a warp and 32 threads declared here, these guys are no ops, but I feel like they are important for correctness. Do not quote me on that, but I feel like they're important for correctness. Right, so now we have moved culling from mesh shader to a task shader. The reason why we did this is now this runs in parallel. So there's a thread that processes 32 meshlets, calls all of them in parallel, writes indices to this buffer, and then starts the mesh workload, right? Which might be faster, but honestly, I'm not really expecting it to be faster, because once again, the amount of work that we do here is so minimal that it will be hard to see the difference, right? But, you know, let's still render. I didn't really take the measurements on the 1,000 kittens after we have done the, oh, yeah. So now what we can do, yeah, yeah. So let's run this thing in release with 1,000 kittens. All right, now let's fix our culling settings so that I really want to see a number that's like telling me, hey, my culling is useful. Because so far we haven't really seen a number that tells us our culling is useful, and that's unfortunate. So I really want to see that. Let us try to see that. So we have flip the culling, and then let us disable debugging here. So now we render. Right, yeah, so we are doing right now like many draw calls. We are doing 1,000 draw calls, but like separately, so it might be really hard to see. Other costs may dominate. Our mesh is relatively large, but also this GPU is really fast. It might be hard to see the benefits. Like this loop at some point will move to the GPU. Oh, and also, yeah, we only have, how many, 320, so it's only 10 groups. Yeah, so it will be really hard to see any benefits on this kitten in our current setup, unfortunately. So that's not great. Let's just end this. Oops. There's some conflict between the whatever extension does GLSL highlighting and the extension that I'm using for Vim emulation. There's some conflict, and they don't, like, not everything works nicely, which is unfortunate. So yeah, there's that. Yes, I don't know if I need the sieve, but fine. Yes, I feel like maybe we are doing making things slower without culling right now. Maybe. On a kitten, it's hard to tell. It's hard to tell. But this might be because we are doing 1,000 draw calls, and then the overhead of starting a draw call up. It is a lot of triangles, so I guess I don't know why that would be the case. And yeah, our problem is we don't really have like a really high poly kitten in a single mesh. We could just replicate the triangles earlier in the pipeline. Yeah, you know what? Whatever. Let's, I guess, focus on not making things slower. Yeah, so this is 0.1-ish, but then it fluctuates a lot. It's unfortunate that yeah, this is roughly the same thing. It's unfortunate that I'm talking about these things that like you should use for improved performance, but then we don't really have content that would accurately reflect these performance gains, and we don't have complete pipeline setup that would allow us to do more sort of more efficient culling with better results, with more things called that would help us realize that these benefits are like significant. Because I think like it should be doable. It's just that, you know, it's a small demo, there's only one mesh, there's no occlusion, there's no nothing, so it's hard to see some of this stuff actually being helpful. But okay, so at least culling works, right? Clearly. Well, not clearly, but let me do this again. So there's that, and then there is that, and then there is that. Okay. So the final thing, we are doing pretty good on time. We are 2 hours 3 minutes in. I want to spend 5 more minutes and try subgroup, or 10 more minutes and try subgroup ups. The driver doesn't have the damage shader. Oh, hello, Christoph. Thank you for joining the stream. Yeah. So I want to do a subgroup code, obviously. Yeah. Let me try. Like on a kitten, the results were different, but okay, let me try this again, because this is interesting, right? Like, why would... Okay, so let's do this again. Backface culling, and then remove crazy visualization, and then in the task shader just disable culling for now, and then yeah, and then render like 10 meshes so that the perf results are more clearly visible. Okay, so we are running like 1.4, 1.5, 1.6, who knows, 1.4 to 1.6. So now let's try to do this really quickly without the stash, because I don't know, maybe that's somehow a problem. So we don't need the task shader. I'm just removing basically the task shader quickly. Remove task shader, remove indexing. I want a profile with culling off. Just to make sure. Yeah, okay, culling was off. So that's fine. It might be 1.6. It was like 1.4 before, but all of these numbers are kind of flaky. Okay, so no task shader, no indexing here, and then render the entire mesh here, and then don't specify the task shader. Yeah. Like we're running with no culling right now, exact same data layout, exact same everything. It's super clear, like just adding a task shader make things faster. So there is the performance recipe for you. Just add the task shader and things will be faster. Alright, so that requires some further investigation. Which we will not do on stream. Okay. Anyway, so yes, I want to do subgroup ops because the atomic is definitely not a great way to do this. Okay, so we have a kitten back. Let's enable culling debugging, so to speak. Oops. Let's enable this. Do rasterization culling. And then actually enable culling. All right. Okay, so here's what I think this can be replaced with. Once again, I haven't done this before, but I understand the concept, and the concept should be simple. So there's this thing introduced in Vulkan, which is subgroup ops that allow you to do some, that allow you to exchange values across threads in your warp. And the extension is based on, you know, somewhat generic definition of all of this stuff. But since we are dealing with NVIDIA hardware right now I will just assume that there's a concept called subgroup width or something like this. Subgroup size, yeah. That is the number of threads that you can exchange. It's like a number of threads in a sort of block of threads, which is a subgroup, right? That you can exchange values between. And there is a bunch of different operations, but one really useful operation is... This is, by the way, a Vulkan subgroup tutorial on Kronos site. Kronos site was dead. Oh, okay, Kronos site is now good. Okay, Kronos site wasn't working in the morning when I opened this tab, but it now does work. So, and we'll have to like enable this extension and stuff like that. So let's actually commit the code that works for culling, double check that it works, disable debugging so that we can commit clean code. Okay. So yeah, we'll clean this stuff later. For now, this is fine. Adding the task shader, and then removing culling from the mesh shader, and then actually adding the task shader. Oh, it will not show it, but fine. Yeah. Day 8, cone, like meshlet, culling, moved to task shader. Also task the sole, presence of the task shader for some reason improves our performance on large meshes like Buddha. I haven't technically benchmarked other meshes, so maybe just Buddha is weird. And also we are doing some things that are still suboptimal, like the memory layout of the meshlet isn't super great. If we have meshlet, most of meshlets have 64 verts, but they don't really go up to 126 triangles, and we aren't compacting this data structure. And we aren't using some intrinsics in the mesh shader, but we've tried to do some of this stuff, like we've tried to do intrinsics and it didn't really help much. But now maybe we'll have to reevaluate all this, because with the task shader we seem to not be running into some weird bottleneck that we were before, which is nice. So yeah, so that's cool. All right, so subgroups. So instead of atomics, we should be able to use a subgroup operation that is called subgroup exclusive add. here's how the subgroup stuff works. So here we were basically saying if the cone test passes, you know, add 1, fill the index, etc. So in theory, of all active invocations, so we cannot do this inside a branch. Well, no, we can do this inside the branch. So yeah, so this is actually beneficial. But then we'd have to do... Christoph told me that I can just copy the code from the blog post from NVIDIA, but I don't want to just copy the code from the blog post. I want to do this myself. Let me just confirm. Yeah, so I think I can just use ballot. The problem is, okay. So here's the code I want to write. I want to... So the spec talks about active invocations, and active invocations I think are the ones that are kind of executing code that is inside the current branch. So what I kind of want to do is I want to do this first. Oops. Oh, come on. What is going on? Hold on. Oh, caps lock, that's enabled. Great. I am wondering, so in theory, if I just do this, well, yeah, should that work? So in theory, if I just do, so exclusive add says it will add the value of the argument in all active invocations, so in all invocations that are actually running, before the current one. So if we are in thread 5, it should add thread 0 through 4, assuming that it actually computed. It may be better to do things. Yeah, let me do this. So if cone culling succeeded, then we want to use if the cone got rejected, so I guess let's call this accept. We want this value, which will be 1 for meshes that are accepted and 0 for meshes that are rejected. So then this should be the index of, it's the sum of all values of accept in threads before our threads, before our thread. So it basically should give us what I want. The only caveat is that we don't want to write this value for groups that aren't, for threads that didn't accept the mesh. So I guess we want to do something like if accept is 1, write the value. Otherwise, just don't touch it, because there will be multiple threads with the same value here. And maybe there can be a branch here that makes this nicer, but for now, let's do it like this. And our final challenge is we need to have the count of these things written. And the count should be, I think we can do this. I mean, we'll have to spend like 5 minutes enabling extensions first. Oh, requires spear v13. Oh boy. Oh boy. Maybe this was too ambitious. All right, so yeah, we're not passing a flag, some flag. Oh yeah, we are using Vulkan 1.1, but we are not passing this flag, I think, which should actually build shaders for Spear v1.3, which is the version that should match Vulkan 1.1. And yeah, so let's fix that. No. Did it actually? Maybe this is not the correct. Let's first build our shader here. Wait. Yeah, so Visual Studio didn't. Oh, is it the usual Visual Studio? Oh, yes. So when you open properties in Visual Studio, it randomly picks a configuration that might be correct or might be incorrect. All right, let's do this again. Okay. Now I'm assuming validate. Why did I not? I don't think we are doing things correctly because I think I saw some problems there, but maybe our code works. I'm surprised I didn't get any validation errors, because I would think you have to enable some of this stuff. I mean, we are using Vulkan 1.1, so that's a plus. But is there really no like subgroup, like boolean something? I'm just so used to having to like specify things 5 times. Is there really no subgroup enable feature something? No? Like feature flag bits? Really? Like you're not supposed to specify this guy anywhere? So this returns the supported bits. So this is what you use to query. But you don't have to enable this at all. Okay. Yeah. So here's what this code does again. It, assuming it works, which it seems to. It says this value is 1 for meshes for meshlets that we have to keep and 0 for meshlets that we have to skip. Then we do an exclusive add, which sums the value of this guy in all threads before ours, which should give us the index into the array that we need to write to. Then we could just write like this, but the problem with that is that we will have several threads. Some of them have meshes that passed and some of them have meshes that failed, conflicting, like sort of concurrently trying to write this data to this array. Let's see what happens if we do this. A different picture happens, right? It doesn't even have to be. I'm guessing maybe the current NVIDIA semantics is that maybe the last write wins. I don't know. Some write wins. So we have to say only write values for the codes that actually have passed, right? And then we don't know the count, but in each thread we know, in the last thread, which is the thread with number 31, we know the sum of all of the values of accept except for the value in the last thread. So this should be correct. There's a different way to do this, which will have an if here, which we can also explore. I'll need to it could use like subgroup max or something like this, but yeah, I don't know what the best way to do this. It's slightly weird to be writing the thing from like the last thread. We're only doing this because the last thread has the exclusive add. But we could be doing, like, we don't have to be doing things like this. We could be using some other subgroup operation, which might be like free. I don't know. Like, for example, we could be using let's see. Where is Max? Yeah. Which extension are we using for this, by the way? Oh yeah, we're using this extension anyway. So we could be doing something like from the first thread we will be writing the max index that was ever written. We will be using the so maybe it will be sort of easier to do things like that, and then nothing works. Really? Really? Really now? Oh, yes. Well, no. Wait. This is weird. It seems like this should have worked. Unless... of all active invocations, but... oh, of all active... oh. Oops. Yeah, okay. So, we could be doing this... yeah, I don't know. There's like many ways to write this code. All we need is a way to communicate data between threads, and all of these subgroup operations give us a way to communicate data between threads. I suspect that the canonical yeah, I suspect that maybe I guess I don't know how you. The other thing we could do is we could use branching, so we could say that the count starts at 0, and then if our cone got accepted, then we'll do the thing that I started with, which is exclusive add 1, which probably works. This will add all ones in all threads prior to my thread, but it should only do this for the threads that are active, which means the threads that have passed the test. So then we'll just write the index, and then we will just do this, and then we'll do this. And then maybe that works as well. Yeah, I don't know what the canonical way to do this is. Let's see. So, GPU clocks. GPU clocks are, so I looked at this before, yeah, so vsync is enabled, but at least as far as the GPU-Z is concerned, the GPU clocks are stable. I think this is because I have set stable power state executable on my machine, but I'm not currently running this. I think OBS just fixes this. We can disable vsync and see if the stability of timings increases at all. This is correct. It's correct that it's missing parts because this is like backface culling without cluster culling that doesn't work super well on this mesh. Yes, I could disable vsync, but I don't know if this will help because it looks like the clocks as reported by GPU-Z anyway are... oh. Okay. Thank you. This is actually very meaningful. This is basically stable. I mean, it's like hovering around 0.1, but this is way more stable than it is with vsync. Interesting. So I guess, yeah, if I don't disable vsync, then even with clocks seemingly stable, they still aren't truly stable. Okay, this is really useful. I wish I knew this before. We will... I can't just use immediate, but let's do this. Let's do FIFO for now, and then to do use immediate if available. Okay. So yeah, there's this ballot thing that may be a more so this will give me a full mask, but then I still need and then I need inclusive bit count, right? Inclusive scans of number of bits. Right, and then I need just bit count. Yeah, okay, yeah, so ballot basically, so I don't really need this stuff, right? It looks like ballot is good enough. I guess this is the canonical way to do this. So we'll do this, we'll do bool accept is not concal. Then we'll do subgroup ballot. Oops, come on. UVec4 ballot is subgroup ballot accept. So this takes all of the booleans and merges them in a giant. So this one is what, I guess this is 128 bits. But on NVIDIA, I'm guessing only 32 bits I used anyway. So then we need an index, which is this inclusive something that we were doing before, which I think is this. So then we need to write, and the write should still be guarded. So if we accept, and then we write, and then the count is just this one. Accept. Rather ballot. So I guess this if this works, it seems to work. Alright, yeah. So I guess this is the canonical way to write this code. Let's do. Something's eating my escape key presses. It's kind of weird. Alright, so yeah, so let's just restore this code briefly so that we know that we are getting correct results. Meshlet indices index mi, and then whoa. The formatting doesn't work in GLSL. Yeah, this extension could have been better for OpenGL highlighting. And then for the first thread, we will write the meshlet count, and then define ballot 0, and then define ballot 1. Alright, yes, so this seems like. Yeah, so that's the same result. Cool. Okay. I guess we'll just keep the ballot version because it's supposed to be the good way how to write this code. The only problem is right now we are sort of assuming that the subgroup size is 32, which happens to be true for NVIDIA, but doesn't have to be true. So this code has to be more complex. There has to be like a loop here or something like that. But for now, this is good enough. I'll just write a to-do comment. We assume that GL subgroup size is 32, same as work group size, which is not necessarily true, but this is our assumption. All right, now let's remove all of the hacks, or specifically just basically flip the culling back to backface culling, and I think that's the only hack that we have right now. Oh, oops. Okay. Okay. We have prematurely. Okay, damn it. Wait, our ballot code doesn't quite work. Do I need exclusive? Exclusive should not count the first one, right? Oh, damn it. Yes, thank you. Sorry. Yes, I mixed them up. Yes, thank you. Yeah, you need an exclusive scan because the exclusive bit count counts all of the bits except for the current one, and inclusive counts all of the bits including the current one. Yes. Okay. All right. Now we can remove the ballot, the non-ballot code, and submit this, and it works. So we have two things to follow up on. One is it's not really clear why the performance got better with task shaders without any culling. So that was fun, but at least we are running faster, meaningfully than the traditional pipeline now. And the other thing that we need to follow up on is it looks like we need to be enabling, disabling vsync basically if we can. You aren't guaranteed to be able to disable vsync in Vulkan, but we need to try, because it looks like our GPU timings are really stable with vsync disabled, but are not stable with vsync enabled despite the clocks being fixed. And I think even if I run set stable power state explicitly, let's check if this is true. Now they don't, well, yeah, so this fluctuates a bit, right? So it jumps up, down. So if I run set stable power state, which I have somewhere here, I think it was roughly the same. Right, so it still sort of randomly jumps up and down. And then if we do immediate, and then it's rock solid. You see it slightly jump, I think between 0.10 and 0.11, but this is because we just don't have enough precision in our output. Like if we do this, then it probably will be nicer. I mean, I guess this makes it worse because it fluctuates, yeah. But this fluctuates between like 0.096 and probably 0.100, which is pretty good. So it looks like we need to do that, which we will do. I just don't want to leave forced immediate because you have to ask if you can use immediate. Alright, so let's submit this code and then we will be done. So to recap, we have implemented cone culling today. We have used task shaders to do cone culling for us. We have discovered that task shaders make some things faster in some cases, which is nice, but weird. And we have done task culling with GLSL atomics, which is like the old way how you are supposed to do these things. And we've done them with subgroup ops, which is the new, faster way how you're supposed to do these things. Use subgroup ops instead of shared memory atomics for culling. This should be faster, even though it's hard to tell right now. I'm wondering if it's actually hard to tell or if we fix the timing problem. I mean, this probably will be the same speed because it's... like, there's not that many meshlets that we are calling. Yeah. Oh, did I save it? Yeah, there's not that many meshlets that we are calling. If you think about this, we have like 11,000 meshlets, and then this means that we have 350 warps running, and it's kind of a small number. So it might be that this doesn't really make that big of a difference in this case, but it's still nice to do this because this is the more appropriate way how to do these things. Alright, so this is it for the stream. We've done everything that we wanted to do, haven't hit any bugs anywhere. Things went really well. And yeah, and that's it. If anybody has any questions, I can spend like 2 minutes answering one or two. But otherwise we are good. All of this code as usual will be on GitHub like soon after the stream, and the video will be on YouTube a few hours after the stream. Oh, NVIDIA driver will replace the atomic with warp intrinsic if it can. So in some cases, so it could be that in our case we can't measure the performance difference, not because there is no performance difference in general, but because NVIDIA driver is smart enough to optimize the atomics here, because it detects, hey, you are running 32 threads in a warp and things like that. So that's nice. That's good to know. Alright, cool. Thank you, and we will continue the streams next week. I have no idea what we are doing next week exactly, but I was thinking that maybe we should start moving in the direction of having more than one mesh on screen and like an actual camera and a depth buffer, and sort of get closer to be able to render a full scene without textures for now, instead of just like one mesh in the center of the screen, which is fun but not always that good, right? Like I want to take something like San Miguel and or like Amazon Lumberyard Bistro scene and start rendering that instead of the single mesh. Alright, thank you, and see you guys virtually next weekend.